The universe is a vast, intricate expanse of mystery and wonder, stretching far beyond the reaches of our imagination. We gaze at the stars, hoping to catch a glimpse of the cosmos's deeper secrets, but it's clear that for every question we answer, many more remain. At the heart of our curiosity lies one of the greatest unknowns of all. What lies at the end of the universe? Is there an edge, a boundary beyond which nothing exists, or does the universe stretch infinitely, its limits beyond our comprehension? This question is not new. It's one that has plagued scientists, philosophers, and dreamers for centuries. As we observe the universe through the lens of our telescopes, we can see galaxies, stars, and nebula, all drifting through the vastness of space. But what happens when we reach the furthest point our instruments can detect? Is that the end, or is there something more, hidden beyond our current understanding? To begin answering this, we must first understand what we mean by the edge of the universe. In traditional terms, we think of an edge as a physical boundary, a place where the universe simply stops. But the universe as we know it does not work this way. It's not like a flat piece of paper where one can clearly see where it ends. Instead, the universe is ever expanding, with galaxies moving away from each other at incredible speeds. This expansion is due to the Big Bang, the event that marks the birth of our universe. The universe began from an infinitely small, hot, and dense point around 13.8 billion years ago. And since then, it has been stretching and expanding, carrying galaxies along with it. This expansion isn't just galaxies moving through space. Space itself is stretching, pushing galaxies further apart. This phenomenon has led to the creation of what we call the observable universe. The observable universe is a sphere centered around Earth with a radius of about 46.5 billion light-years. This number seems counterintuitive at first, especially when we remember that the universe is only 13.8 billion years old. How can we observe light that has traveled more than 46 billion light-years when the universe hasn't existed that long? The answer lies in the expansion of space itself. As the universe expands, the space between objects also grows. This means that light from distant objects travels through expanding space, so it has to cover a greater distance than one might expect. Therefore, the observable universe extends far beyond the distance that light has been able to travel in the 13.8 billion years since the Big Bang. And yet, this is just the observable part of the universe, what we can see with our most powerful telescopes. Beyond this observable universe, we are blind. We can't see, touch, or detect anything beyond the 46.5 billion light-year mark. But that doesn't necessarily mean that the universe ends there. In fact, we have no way of knowing what lies beyond because light from those regions will never reach us. This is where the concept of cosmological horizons comes in, marking the limits of what we can observe. One such horizon is the particle horizon. This is the furthest distance from which light could have traveled to reach us since the beginning of the universe. It essentially defines the edge of the observable universe. But there's another horizon called the event horizon. This horizon marks the point beyond which objects are receding from us so quickly that no signal or information can ever reach us, not even light. This means that once something crosses this boundary, it becomes permanently invisible to us. These horizons are not just theoretical constructs. They represent the practical limits of our ability to perceive the universe. Imagine standing at the edge of a vast ocean, gazing out over the water. You can see the horizon where the ocean seems to meet the sky, but you know that beyond it lies more water, more ocean. In the same way, our view of the universe is limited by the horizons we can see. Beyond them, there's more. We just can't see it. The idea of the event horizon is particularly important when we think about the future of the universe. The universe is expanding at an accelerating rate, driven by a mysterious force known as dark energy. As the universe expands, galaxies that are currently visible to us will eventually drift beyond our reach. Over time, more and more of the universe will fall beyond our observable horizon, leaving us with an increasingly isolated view of the cosmos. This isolation will only continue to grow as the universe ages. Eventually, even the nearest galaxies will become unreachable, their light forever cut off from us. In this scenario, the universe would appear to be empty, with only the local group of galaxies remaining visible. It would be a cosmic island, isolated in the vast sea of space. But this is not the end of the story. The universe is full of strange and mysterious phenomena, and the further we look, the more questions arise. Are there other universes beyond our own? Could the universe be infinite, with no true end in sight? These are questions that we may never have answers to, but they continue to push the boundaries of our understanding. As we continue to explore the mysteries of the universe, it's essential to understand the concepts that shape our view of what's possible. We've discussed the observable universe and the horizons that limit our perception, but beyond these boundaries lies a far more complex and intriguing landscape. In our attempt to understand the universe, we come across another profound question. Is the universe infinite, or does it have an end? The idea of infinity is both awe-inspiring and unsettling. The notion that the universe could stretch on forever with no end in sight challenges our understanding of space, time, and reality itself. If the universe is infinite, then the implications are profound. It would mean that no matter how far we travel, there will always be more universe to explore. But what does it mean for the universe to be infinite? How does infinity work in the context of space? One possible answer lies in the shape of the universe. The universe, as we know, is not flat, but rather it has a curvature. This curvature is determined by the overall density of matter and energy in the universe. If the universe is dense enough, its curvature will cause it to eventually close upon itself, like the surface of a sphere. In this case, the universe would be finite, but without an edge, much like the surface of the Earth. You could travel in one direction indefinitely, but you would eventually return to your starting point. However, the latest observations suggest that the universe is flat, or at least very close to flat. This means that the universe could extend infinitely in all directions, with no inherent curvature to bring it back on itself. If this is the case, the universe would have no edge and would continue on forever, with galaxies, stars, and other cosmic structures spreading out endlessly. But even if the universe is infinite, that doesn't necessarily mean it's eternal. The fate of the universe depends largely on its expansion. As we've seen, the universe is expanding at an accelerating rate, driven by dark energy. This acceleration means that, over time, galaxies will continue to drift further apart, and the universe will become more and more spread out. Eventually, the galaxies that we see today will be so far away that we won't be able to detect their light, even with the most advanced telescopes. In this future, the universe will become dark and cold, a place where stars burn out and galaxies drift into isolation. This scenario, known as the heat death of the universe, is one possible outcome of the universe's expansion. In this state, all matter will be evenly distributed, and the universe will be devoid of any significant structures. It will be a place where nothing happens, a quiet, empty void. But even this is not the final word. Some scientists propose an alternative to the heat death scenario, the possibility of a big freeze. In this scenario, the expansion of the universe continues to accelerate, causing galaxies to move further apart at an increasing rate. Eventually, this acceleration would cause space itself to stretch beyond the point where even light can travel, leaving only a handful of objects, such as black holes, remaining in a dark, frozen universe. As we consider these possibilities, we must also entertain the idea that there may be a greater cosmic cycle at play, one that we cannot yet fully comprehend. Some theories suggest that the universe undergoes periodic cycles of birth, death, and rebirth, a process known as the Big Bounce. In this scenario, the universe would collapse back in on itself after a period of expansion, only to rebound in a new Big Bang, starting the cycle over again. This cyclical model raises interesting questions about the nature of time itself. If the universe is continually reborn, does that mean that time has no true beginning or end? Is our universe just one chapter in an infinite series of cosmic events? The idea of the Big Bounce suggests that the universe could be eternal, oscillating between moments of creation and destruction. But even this theory is not without its mysteries. The exact mechanism that would cause the universe to collapse and rebound remains unclear, and much more research is needed to fully understand the implications of this concept. Beyond these cyclical theories lies yet another possibility: the multiverse. The idea of the multiverse proposes that our universe is just one of many, each existing in its own bubble of space-time, with its own physical laws and constants. If this is the case, then the end of our universe may not be the end at all. Instead, it could simply be the beginning of another universe, one with different rules and structures, far beyond our comprehension. The multiverse theory opens up a whole new realm of possibilities. If there are an infinite number of universes, each with its own set of physical laws, then the concept of an end becomes irrelevant. Our universe may be just one of countless others, each existing in parallel with our own. And yet, the idea of the multiverse also raises profound philosophical questions. If there are infinite universes, does that mean that anything and everything is possible? Could there be a universe where everything we know is turned upside down, where the laws of physics are completely different from our own? The more we explore these theories, the more we realize that the end of the universe is not a simple concept. It is a question that touches on the very nature of existence itself. Is the universe finite or infinite? Does it have a true end, or does it stretch on forever? And if it does end, what lies beyond that? And these are questions that may never be fully answered, but they push us to think beyond our current understanding, to challenge the boundaries of what we know, and to continue our quest for knowledge. To understand the nature of the universe's end, we must first consider the forces that govern its expansion. The universe is not a static entity. It is constantly changing, evolving, and stretching outward, propelled by forces that we are only beginning to comprehend. The key to understanding these forces lies in the study of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy accounts for around 68% of the total energy content of the universe, yet we still know very little about it. All we know is that it acts in opposition to gravity, pushing galaxies apart instead of pulling them together. The discovery of dark energy has profoundly changed our understanding of the universe's future. Before dark energy was discovered, scientists believed that the expansion of the universe would eventually slow down, driven by the gravitational pull of matter. However, the discovery of dark energy has led to a new understanding. The universe will continue to expand, and it will do so at an accelerating rate. This acceleration is not just a theoretical concept. It has been observed in the motion of distant galaxies. By studying the light emitted by supernovae, astronomers have noticed that galaxies are moving away from us faster than we initially thought. The implications of this discovery are immense. If the universe continues to expand at an accelerating rate, it will eventually reach a point where galaxies become so distant that they are no longer visible to us, even with the most advanced telescopes. This point marks the beginning of an era known as the Cosmic Dark Age. In this dark age, all the familiar structures we associate with the universe, galaxies, stars, planets, will be gone. Stars will burn out, and galaxies will be dispersed across an ever-expanding void. The universe will become a place of cold darkness, where light can no longer travel across vast distances. This is the future that awaits us if the universe continues to expand forever, driven by dark energy. But what exactly causes dark energy to behave in this way? Scientists have several theories, but none of them can fully explain its properties. One possibility is that dark energy is related to the vacuum of space itself. According to the theory of quantum mechanics, even empty space is not truly empty. Instead, it is filled with virtual particles that constantly pop in and out of existence. This vacuum energy could be responsible for the repulsive force we observe as dark energy. However, this theory remains speculative, and more research is needed to understand the true nature of dark energy. Another possibility is that dark energy is a manifestation of a fundamental force of nature, one that we have yet to discover. Some scientists have proposed that dark energy could be related to the properties of extra dimensions, suggesting that the universe we observe is only one part of a much larger multi-dimensional reality. If this is the case, the ultimate fate of the universe could depend on the nature of these extra dimensions and how they interact with our own. Regardless of its origin, dark energy plays a crucial role in shaping the future of the universe. As the force behind the accelerating expansion of the universe, dark energy ensures that galaxies will continue to drift apart and that the universe will grow colder and darker with each passing moment. But what happens when the universe reaches this state of isolation? What does the end of the universe look like in practical terms? In this far future scenario, galaxies will become increasingly distant from each other, making the universe seem empty and desolate. Over billions of years, stars will burn out, and the remnants of stellar death, white dwarfs, neutron stars, and black holes, will persist, but they too will eventually fade. Black holes, those enigmatic objects with gravity so strong that not even light can escape, will slowly lose their mass through a process known as Hawking radiation. Hawking radiation, a theoretical concept proposed by physicist Stephen Hawking, suggests that black holes can emit radiation due to quantum effects near their event horizons. Over an incredibly long period of time, this radiation causes black holes to lose mass and energy, ultimately leading to their evaporation. This process would take longer than the current age of the universe, but eventually all black holes would disappear, leaving behind a cold, empty void. In the absence of stars and black holes, the universe would consist primarily of diffuse particles, atoms, photons, and dark matter. These particles would be spread so thinly across space that they would rarely interact with one another. In this state, the universe would be a vast, lonely place where even the faintest glimmer of light would be impossible to see. It would be a universe without motion, a universe where time itself seems to slow down and lose meaning. As the universe continues to expand, the effects of this expansion will become more pronounced. Space itself will stretch and galaxies will become more and more isolated. The space between galaxies will continue to grow, eventually surpassing the speed of light. This is due to the nature of cosmic expansion. It's not limited by the speed of light. While objects within a galaxy can't exceed the speed of light, the space between galaxies can. This means that distant galaxies will eventually become unreachable, even if we could travel at the speed of light. As galaxies recede from us, the light emitted by them will be redshifted, stretched to longer wavelengths due to the expansion of space. This redshifting will cause the light to fade, making distant galaxies increasingly difficult to observe. Over time, the universe will become a place where the light from other galaxies is no longer detectable, and we will be left with a solitary view of our own local galaxy. This scenario, known as the isolation era, paints a picture of a future universe that is cold, dark, and devoid of significant structures. It is a universe that will continue to expand, but without the rich variety of stars, planets, and galaxies that we see today. This future may seem bleak, but it is also a reminder of the impermanence of all things, even the universe itself. To further understand the fate of the universe, we must consider another key factor in its eventual demise: the ultimate fate of matter. While dark energy drives the universe's accelerated expansion, matter, both ordinary and dark, plays a significant role in the structure and behavior of the cosmos. How matter behaves in the far future will have a profound impact on the universe's ultimate destiny. As we've seen, stars burn out and galaxies drift apart in the distant future. But matter doesn't simply vanish. It undergoes a slow, inexorable transformation. After the stars exhaust their nuclear fuel, they become white dwarfs, neutron stars, or black holes. These remnants of dead stars are all that will remain of the once vibrant, glowing objects that populated the universe. Over billions of years, these objects will gradually fade and cool, their energy slowly dissipating into the cold, empty void. For white dwarfs, the process of cooling and fading is a long one. Over a period of about 10 billion years, a white dwarf will gradually lose its heat and become a cold, dark object known as a black dwarf. However, this process will take longer than the current age of the universe, so black dwarfs will not exist for billions of years to come. Even when they do eventually form, they will be almost impossible to detect, as they will emit no light and will be near absolute zero in temperature. Neutron stars, the remnants of more massive stars, will also undergo a gradual transformation. These dense, compact objects are primarily composed of neutrons and are held together by gravity. While neutron stars do not radiate light in the same way as normal stars, they can emit radiation through other means, such as through their magnetic fields. Eventually, however, even these emissions will fade, and neutron stars will lose their energy. The most enigmatic remnants of stellar death, however, are black holes. These cosmic giants, formed when massive stars collapse under their own gravity, are the most powerful objects in the universe. Their gravitational pull is so strong that not even light can escape their event horizon, making them invisible to direct observation. However, black holes are not permanent. Over time, they will lose mass through Hawking radiation, the theoretical process by which black holes slowly evaporate. Hawking radiation, as proposed by physicist Stephen Hawking, suggests that black holes are not entirely black. Instead, they emit radiation due to quantum mechanical effects near their event horizons. This radiation causes black holes to lose mass and energy, gradually shrinking and eventually disappearing. While this process takes an incredibly long time, far longer than the current age of the universe, it is inevitable. In the end, all black holes will evaporate, leaving behind a universe devoid of the massive, mysterious objects that once dominated it. With the disappearance of black holes, the universe will continue its journey toward entropy. Entropy, the measure of disorder in a system, is a fundamental concept in thermodynamics. In the context of the universe, it means that over time, the cosmos will move toward a state of maximum disorder and energy dispersion. This process is known as the heat death, or big freeze of the universe. As entropy increases, the energy available to do work decreases. In the far future, this will lead to a universe that is no longer able to support complex processes or structures. Stars will have burned out, black holes will have evaporated, and galaxies will be too far apart to interact. The universe will become an expanse of cold, empty space with no sources of energy to fuel the processes that sustain life or matter as we know it. This state of maximum entropy is not just a theoretical concept, it is a fundamental law of physics. The second law of thermodynamics states that in any closed system, entropy will always increase over time. The universe, as a whole, is a closed system, and so it too will inevitably reach a state of maximum entropy. In this state, all processes will cease, and the universe will be as cold and lifeless as possible. However, there is still one final mystery that remains to be explored: the nature of dark matter. While dark energy makes up the majority of the universe's energy content, dark matter is the elusive substance that accounts for about 27% of the universe's total mass. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to direct observation. Yet its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Dark matter plays a crucial role in the structure of the universe. It acts as a kind of cosmic glue, holding galaxies together and preventing them from flying apart due to their high velocities. Without dark matter, galaxies would not have the mass needed to form and maintain their structures. But what happens to dark matter in the far future? Currently, the nature of dark matter is one of the biggest mysteries in cosmology. Scientists have proposed several theories about what dark matter might be, including exotic particles like WIMPs, weakly interacting massive particles, or axions. However, no direct detection of dark matter has been made, and its true nature remains elusive. As the universe continues to expand and galaxies drift apart, it's possible that dark matter will play an increasingly important role in the universe's fate. Some theories suggest that dark matter could eventually decay or be transformed into other forms of energy. If this happens, it could alter the universe's trajectory, potentially leading to a new phase of cosmic evolution. But for now, dark matter remains an enigma, a hidden force that influences the universe in ways we are only beginning to understand. Even as the universe continues to expand and matter slowly fades into darkness, the question remains: is this the true end of the universe? Or is there something more, something beyond the reach of our current understanding? As we peer into the depths of space and time, we are reminded of the vast unknowns that still lie ahead. The end of the universe may be inevitable, but the journey to understand it is far from over. One of the most fascinating aspects of the universe is its vastness and complexity. The very structure of the universe, from galaxies to galaxy clusters, gives us clues about the future evolution of the cosmos. We've already touched on the fate of individual stars, black holes, and even galaxies, but the larger scale structure of the universe must also be considered. Over the course of cosmic history, the universe has grown from a dense, hot state to the vast, sprawling expanse we observe today. And as the universe continues to expand, its large-scale structure will also evolve. Currently, the universe is composed of vast networks of galaxies, each containing billions of stars. These galaxies are not distributed randomly across space. Instead, they form large structures known as the cosmic web. This web consists of long, thin filaments of galaxies separated by vast voids of nearly empty space. These filaments and voids make up the large-scale structure of the universe, a pattern that has been shaped by gravity and the distribution of matter over billions of years. As the universe continues to expand, the cosmic web will change. The filaments of galaxies will stretch as galaxies move farther apart due to the accelerated expansion driven by dark energy. Over time, these filaments will become more diffuse, with galaxies slowly drifting away from one another. Eventually, galaxies will be so far apart that the structures we now see, the vast webs of galaxies, will no longer be recognizable. Instead, the universe will become an isolated collection of distant, independent objects. This process is already happening. The expansion of the universe is not uniform. Some regions of space are expanding faster than others. In particular, distant galaxies are receding from us at increasing speeds due to the influence of dark energy. As a result, the large-scale structure of the universe is stretching out over time. Eventually, the cosmic web will break down, and the universe will become a collection of isolated galaxies with no hope of future interactions or mergers. The fate of galaxy clusters is another intriguing aspect of the universe's future. Galaxy clusters, which are made up of hundreds or even thousands of galaxies, are the largest gravitationally bound structures in the universe. These clusters are held together by gravity, and their constituent galaxies interact and merge over time. However, as the universe expands, galaxy clusters will begin to break apart. The galaxies within them will drift away from one another, and the clusters will gradually dissolve. This process will take billions of years, but in the end, galaxy clusters will become a distant memory, leaving behind isolated galaxies. In the far future, these isolated galaxies will no longer be able to interact with one another. There will be no more galactic mergers, no more formation of new stars, and no more cosmic events that generate energy. The universe will become a cold, dark place, with each galaxy drifting aimlessly through the vast emptiness. Even within these isolated galaxies, star formation will cease as the remaining gas is exhausted. Without new stars being born, galaxies will eventually fade into obscurity, with only the remnants of their former selves, white dwarfs, neutron stars, and black holes, remaining. At this point, the universe will enter a period known as the degenerate era. During this time, the universe will be dominated by dead stars and black holes. Most of the matter that once formed vibrant stars and galaxies will have been turned into dark remnants, and the universe will be a quiet, desolate place. The galaxies that remain will be faint, with only the faintest glow from the dying stars within them. One of the key features of the degenerate era is the gradual cooling of the universe. As time passes, the universe will continue to expand, and the remaining matter will lose energy. The temperature of the universe will drop, and the once violent cosmic processes that gave birth to stars, galaxies, and planets will become a distant memory. The remnants of stars, white dwarfs, neutron stars, and black holes will continue to cool and fade, and the universe will become an ever colder, more inhospitable place. In this era, black holes will dominate the landscape. These mysterious objects, which were once rare and exotic, will become the most important structures in the universe. As stars and galaxies fade away, black holes will be the last remnants of the once bustling cosmos. They will continue to grow as they consume the remaining matter in their vicinity, but eventually they will run out of fuel. The last black hole will slowly evaporate through Hawking radiation, and the universe will be left in a state of near-total darkness. The process of black hole evaporation, as proposed by Stephen Hawking, is incredibly slow. A black hole with the mass of the Sun would take on the order of 10^67 years to fully evaporate. This means that even the most massive black holes will persist for an inconceivably long time before they finally disappear. In the end, however, even black holes will cease to exist, leaving behind a universe that is empty, cold, and devoid of structure. It's important to note that this scenario, the complete evaporation of black holes and the heat death of the universe, is not the only possibility. There are other theories about the ultimate fate of the universe, some of which propose alternative endings. For example, some cosmologists suggest that the universe could eventually collapse in on itself in a process known as the Big Crunch. Others propose the idea of a big rip in which dark energy causes the universe to expand at an ever-increasing rate, ultimately tearing apart galaxies, stars, and even atoms. However, the heat death scenario remains the most widely accepted theory. It is supported by the laws of thermodynamics and the observed behavior of the universe. As the universe continues to expand, it will inevitably reach a state of maximum entropy, where all energy is evenly spread out and no more work can be done. In this state, the universe will be a lifeless, frozen expanse with no possibility for new stars to form or for any meaningful interactions to occur. The ultimate fate of the universe, then, seems to be one of isolation, cold, and darkness. As the galaxies fade, the stars die, and the black holes evaporate, the universe will become a place where nothing new can happen. All that will remain is a quiet, empty void, where the passage of time becomes irrelevant. The universe will have reached its end, not in a dramatic explosion or sudden event, but in a slow, gradual decline toward entropy. As we contemplate the end of the universe, we are reminded of the vast scale of time and space. The universe is a place of infinite possibility, but it is also a place of inevitable decay. The forces that govern the cosmos are not eternal. They are subject to the same laws of thermodynamics that govern all matter and energy. And in the end, these laws will ensure that the universe reaches a state of maximum disorder, a state where time itself loses its meaning. It's worth considering that the eventual death of the universe may not be a singular event. Instead, it will be a series of gradual processes unfolding over billions or even trillions of years. One such process is the fate of the remaining stellar remnants, the white dwarfs, neutron stars, and black holes that will remain long after stars have died. These remnants will continue to evolve over immense stretches of time, eventually contributing to the final stages of the universe's demise. White dwarfs, for example, are the remnants of low to medium mass stars. After their fuel is exhausted, these stars shed their outer layers and leave behind a dense, Earth-sized core. Over time, the white dwarf will cool, its surface temperature gradually lowering. Initially, these stellar remnants will emit faint amounts of light and heat, but this energy will eventually dissipate. After billions of years, the white dwarf will become a cold, dark object, essentially a black dwarf. However, this transformation is so slow that it will take far longer than the current age of the universe for this process to occur. Meanwhile, neutron stars created by the collapse of massive stars in supernova explosions are even more extreme. A neutron star's density is so high that a single cubic centimeter could weigh several billion tons. These stars will remain hot for a long time, but as time progresses, they too will cool down. They will emit less radiation and eventually become black neutron stars, cold and invisible to the naked eye. This, however, will also take a period of time that far exceeds the universe's current age. Eventually, neutron stars will fade in the cosmic darkness, leaving behind nothing but emptiness. The ultimate stage in the life cycle of matter, however, is the black hole. These objects, formed from the collapse of the most massive stars, are defined by their event horizons, the points beyond which nothing, not even light, can escape. Black holes will continue to exist long after the stars have disappeared, as their immense gravity keeps them intact. Over time, they will continue to grow by absorbing matter from their surroundings, including any remaining gas, dust, or stellar remnants that might drift too close. But black holes are not eternal either. In the 1970s, the physicist Stephen Hawking proposed that black holes gradually lose mass through a process known as Hawking radiation. According to this theory, black holes emit radiation due to quantum effects near their event horizons, causing them to slowly lose mass and energy over time. This process is incredibly slow, with a large black hole like the one at the center of our galaxy, Sagittarius A*, taking longer than the current age of the universe to evaporate entirely. Smaller black holes, however, would evaporate much more quickly, potentially in just a few trillion years. As black holes continue to shrink due to Hawking radiation, they will eventually reach a point where they evaporate completely, leaving behind nothing but radiation. The universe will have gone from a hot, dense state filled with stars, galaxies, and dynamic processes to a cold, dark void populated only by remnants of matter and radiation. The last black hole will fade away, and all that will remain in the universe is the faint glow of leftover energy, slowly losing its strength. While the universe may seem empty during this stage, it's important to note that there will still be quantum processes at play. Even in a cold, dark universe, the laws of physics will continue to operate. At the quantum level, particles will still interact, though these interactions will be incredibly rare and insignificant on a cosmic scale. Over time, the temperature of the universe will approach absolute zero, and all matter will be frozen in a state of inertness, with no energy available to sustain life or even matter itself. In this deep cosmic future, even the concept of time becomes blurred. As the universe continues to expand and entropy increases, time itself may stretch into infinity, as there is no longer any meaningful way to measure it. The universe will continue to exist, but it will be devoid of life, movement, or any significant change. This state of eternal stasis is what many refer to as the heat death of the universe. A universe so far removed from its origins that all processes have ceased, and the only thing left is a silent, infinite void. But what if the universe could find a way to escape this fate? Some theories suggest that the universe could undergo a dramatic transformation at the end of this long, slow march toward entropy. The idea of a big rip is one such possibility, though it stands in contrast to the heat death scenario. According to the Big Rip theory, the force of dark energy could continue to accelerate, eventually tearing apart galaxies, stars, planets, and even the fabric of space-time itself. In this scenario, the universe would end not in a gradual fade, but in a violent and catastrophic destruction of all matter and energy. While the Big Rip theory remains speculative, it serves as a reminder of the fundamental unpredictability of the universe's ultimate fate. There are still many unknowns when it comes to the true nature of dark energy, the forces that govern cosmic expansion, and the eventual destiny of everything we see around us. Could the universe eventually collapse in on itself, in a process known as the Big Crunch? Could it undergo a quantum leap into a new phase of existence, as some have speculated, or will it simply fade away into the darkness, never to be heard from again? The reality is that we may never know the true fate of the universe, at least not in our lifetimes. The vast scale of time involved makes it difficult to predict with any certainty what will happen to the universe in the distant future. What we do know, however, is that the universe is a dynamic, ever-evolving entity, and its future is as full of mystery as its past. As we continue to study the universe, we gain a deeper understanding of its structure, its history, and its potential future. But no matter how much we learn, we are still left with the same fundamental question: what lies at the end of the universe? The answer, perhaps, is not one that can be easily grasped. It may not be a single event or a simple conclusion, but rather a series of complex processes that unfold over unimaginable spans of time. The final stages of the universe bring with them a paradox, a tension between the known and the unknown. Despite all the knowledge we have amassed, the future of the universe remains largely speculative, with a multitude of competing theories about its ultimate destiny. One of the most significant challenges we face when contemplating the end of the universe is the idea of infinity. The universe is vast, and yet it may also be infinite. If the universe extends forever, then what does it mean for something to end? Can we truly imagine a boundary to infinity, a point beyond which nothing exists? The very concept of an edge to the universe seems to defy our understanding of space and time. After all, if the universe is infinite, how can we even talk about an end in the traditional sense? This is where the theories about cosmic expansion and dark energy come into play. As we discussed earlier, the universe has been expanding ever since the Big Bang. This expansion is accelerating, driven by a mysterious force known as dark energy. If this expansion continues indefinitely, it could lead to a scenario in which galaxies and stars are so far apart that they are no longer visible or detectable from one another. The universe could stretch into an ever-widening, ever more isolated void, with each object moving away from every other object. But even in this scenario, the end of the universe may not be a clear-cut event. Instead, it would be a gradual process, a slow unwinding of the cosmos into a state of near complete isolation. Imagine a universe so vast that even though it still exists, there is no interaction between its components. No galaxies, no stars, no planets, just isolated pockets of space, each alone in its own bubble of existence. This isolation would stretch the very fabric of space itself, causing everything to drift farther and farther apart. This idea of a lonely universe is one of the most poignant aspects of the eventual end. As the stars fade and black holes disappear, what remains will be the cold remnants of what once was, a universe that was once filled with life, movement, and light, now silenced by the relentless march of time. The passage of time will become even more abstract as the universe becomes so diffuse that nothing ever interacts with anything else. In a sense, this would be the universe's entropy phase. Entropy, as we know, is a measure of disorder, and in a universe that continues to expand, the disorder increases. Eventually, all the stars will burn out, all the black holes will evaporate, and any matter left behind will decay into subatomic particles, slowly losing any ability to do work. The universe will have reached a state of maximum entropy where no more meaningful processes can occur, and everything is in a state of thermal equilibrium. While this scenario sounds bleak, it is important to note that there is an underlying beauty in the concept of universal entropy. It represents the ultimate conclusion of the universe's journey, where all things, regardless of their origin or complexity, return to the same state of uniformity. No matter how diverse the cosmos was at its peak, it will ultimately succumb to this universal fate. The stars, galaxies, and planets will all eventually fade into nothingness. But the universe itself, in its final moments, will become a quiet, still place, free of conflict, change, and even light. This concept of universal stillness may seem like the end of everything, but it also holds a deep philosophical implication. Perhaps the true end of the universe is not a singular event, but a process, a gradual winding down that allows for a peaceful conclusion. It might be a death without chaos, without cataclysm, just a slow fading into nothingness. In this sense, the universe's end may not be a moment of destruction, but a slow and quiet surrender to the inevitable forces of time. However, some theories challenge the idea of an infinite, expanding universe heading toward inevitable entropy. The concept of a cyclic universe offers an intriguing alternative. In this model, the universe does not end in a single irreversible state, but instead undergoes a series of expansions and contractions. After each cycle, the universe could potentially reset itself, leading to a new Big Bang and the creation of a new universe. This cyclical process, often referred to as the Big Bounce, suggests that the universe could go through infinite cycles of birth and death, each one possibly different from the last and potentially leading to new forms of life, new structures, and even new laws of physics. If the cyclic model holds true, it would mean that the end of our current universe is merely a prelude to the birth of something new. The cosmic energy that would be released in such a transition might seed a fresh universe, potentially with different properties or even new dimensions of space and time. This idea offers a sense of hope, a cosmic rebirth instead of an ultimate death. The cyclic model, however, also raises more questions than answers. How exactly would the universe bounce back after its collapse? What forces would govern the transition from one cycle to the next? And what happens during the time between cycles, when there is no observable universe and no structure at all? The answers to these questions remain elusive, as our understanding of the universe's deepest mysteries is still incomplete. But what is clear is that no matter what the fate of the universe turns out to be, whether it ends in quiet isolation, an infinite cycle, or something even more unexpected, it will always remain an enigma, an unsolvable puzzle that challenges our understanding of reality itself. As we consider the fate of the universe, it's crucial to acknowledge that these scenarios are based on current scientific theories. Future discoveries, breakthroughs in quantum mechanics, or new insights into the nature of dark energy could radically change our perspective. The universe may hold secrets we have yet to uncover, ideas and forces beyond our current comprehension. As we continue our deep dive into the universe's final stages, we now shift focus to the role of black holes, enigmatic and mysterious structures that serve as cosmic endpoints for matter. They are not merely objects of interest, they may also hold the key to understanding the universe's fate. These regions of space, where gravity is so intense that nothing can escape their pull, have fascinated astronomers for decades. Their existence challenges our understanding of physics, and their ultimate role in the universe's future remains a topic of ongoing debate. Black holes are formed when massive stars collapse under their own gravity at the end of their life cycles. Once a star runs out of fuel, it can no longer support itself against the immense pressure of gravity. The star's core collapses and a singularity is formed, a point of infinite density surrounded by an event horizon, the boundary beyond which not even light can escape. What happens inside this boundary is still a mystery, but the presence of black holes in the universe has profound implications for its future. In the far distant future, black holes could play a crucial role in the ultimate demise of the universe. One theory suggests that as the universe expands and matter becomes more and more dispersed, black holes could become the last remaining structures holding any significant mass. These supermassive black holes, located at the centers of galaxies, could continue to grow as they consume the surrounding matter. Over time, however, even black holes are not invincible. They are subject to a process known as Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in the 1970s. Hawking radiation suggests that black holes gradually lose mass and energy over time by emitting particles, a process that eventually causes them to evaporate. The larger the black hole, the slower this process occurs. But in the distant future, all black holes, even the most massive ones, will eventually evaporate completely. As they do, they will release energy in the form of radiation, and all that will remain is the ghostly imprint of their once mighty gravitational influence. The evaporation of black holes marks the end of an era where these cosmic giants were the last significant players in the universe. The process of Hawking radiation will likely take an unimaginably long time, far beyond the current age of the universe. For instance, it is estimated that the most massive black holes could take a staggering 10 to the 100 years to fully evaporate. But once they're gone, the universe will be left with little more than scattered particles and a faint residual heat from the cosmic microwave background radiation. In the absence of black holes and other matter, the universe will enter what is known as the degenerate era, a time when stars no longer shine and galaxies no longer collide. This era will stretch for an immense period, possibly longer than the current age of the universe. During this time, the universe will be a barren place, with only remnants of what once existed. Neutron stars and white dwarfs, the remnants of dead stars, will slowly cool and fade away, leaving nothing behind but the faint whispers of a once vibrant cosmos. As this process continues, the universe will be dominated by dark energy, the mysterious force responsible for the accelerated expansion of the cosmos. Dark energy seems to be pushing galaxies apart at an ever-increasing rate, and as it becomes more prevalent, it could eventually lead to what is called the Big Freeze. In this scenario, the universe will continue to expand indefinitely, with galaxies, stars, and planets moving farther and farther away from each other. The light from distant stars will fade into the darkness, and the universe will become increasingly cold and desolate. In this cold, dark universe, life as we know it will be impossible. This final phase of the universe's existence, where stars burn out, black holes evaporate, and galaxies drift into oblivion, offers a chilling vision of the end of time. But it is not the only possible future for the universe. While the Big Freeze is one of the most widely accepted scenarios, there are alternative theories that offer different possibilities. One of the most intriguing alternatives is the Big Crunch, a scenario in which the expansion of the universe eventually reverses and gravity causes everything to collapse inward. In this model, the universe would contract, drawing all matter and energy back into a singularity. This collapse would lead to a final catastrophic event, a Big Bang in reverse. If the Big Crunch were to occur, it could potentially be followed by another Big Bang, initiating a new cycle of cosmic evolution. This cyclic model of the universe offers a dramatic counterpoint to the idea of an eternal, expanding universe that eventually fades into nothingness. The Big Crunch, however, hinges on the total amount of matter and energy in the universe. If there is enough mass to halt the expansion and reverse it, then the universe would collapse in on itself. But if dark energy continues to dominate the expansion as current observations suggest, then the universe will keep stretching outward, and the big crunch may never happen. There are also other theories that speculate on the nature of the universe's fate, such as the Big Rip. In this scenario, the expansion of the universe continues to accelerate until it reaches a point where the fabric of space-time itself is torn apart. This would cause galaxies, stars, planets, and even atoms to disintegrate, leaving nothing behind but pure energy. The Big Rip is a catastrophic and violent end to the universe, and while it is an unlikely outcome based on current evidence, it remains one of the potential fates of the cosmos. Ultimately, no one can predict with certainty what will happen at the end of the universe. Whether the universe ends in a slow fade, a collapse, or a violent tear, the truth is that we are only beginning to scratch the surface of this profound question. As we continue to study the cosmos and unlock its deepest secrets, we will no doubt encounter new ideas and theories that will challenge our current understanding. The end of the universe is, in many ways, a reflection of the limitations of human knowledge, and it remains one of the most awe-inspiring mysteries of all. As we move further into the unknown, we now turn our attention to the potential for life, or rather, the absence of it, in the universe's final stages. When we think about the future of the cosmos, the survival of life may seem like a distant possibility, especially as conditions begin to change drastically. Whether it's the depletion of stars, the expansion of space, or the gradual cooling of the universe, life, as we understand it, may not be able to endure for long in this evolving environment. But before we assume that all life must end with the universe, it's important to examine how life has survived in some of the most extreme conditions here on Earth. Extremophiles, organisms that thrive in conditions that would be fatal to most other life forms, offer a glimpse of the resilience of life. These organisms have been discovered in places like deep-sea hydrothermal vents, acidic hot springs, and the frozen extremes of Antarctica. If life can exist in these harsh environments on Earth, could it also find a way to endure in the far-flung future of the universe, where conditions become ever more hostile? While the universe itself is becoming colder and emptier, certain theoretical scenarios suggest that some forms of life may still find a way to survive. For instance, in the far-off future, as stars burn out and galaxies drift further apart, it's possible that the remaining pockets of life could exist in isolation, shielded from the increasingly inhospitable conditions. One possibility is the existence of civilizations or organisms living near the remnants of stars, perhaps harnessing the last flickers of energy from dying suns, or tapping into the cosmic microwave background radiation that will persist for eons. This kind of life might be drastically different from anything we know today, adapted to the low temperatures and scarce resources of an isolated universe. However, even in these isolated refuges, life would eventually face the inevitable, the total extinction of usable energy. As stars and black holes evaporate, even these distant pockets of existence would be forced to reckon with the fundamental limits of energy. Without new energy sources to replenish themselves, even the hardiest forms of life would ultimately succumb. The universe's fate as a cold, dark, and energy-depleted space will make it increasingly difficult for life to maintain itself over time. This scenario is known as the heat death of the universe, a state in which the universe reaches maximum entropy, where all energy is evenly distributed and no work can be done. In this state, all physical processes would cease. Matter would decay into fundamental particles, and the last remnants of life would fade away into the infinite cold. The heat death is often viewed as the ultimate endgame for the universe, where all systems have run out of energy and no further change can occur. It is, in essence, the final step toward cosmic equilibrium, but one that is devoid of anything resembling life or activity. Yet, even within this bleak scenario, some scientists speculate about the possibility of life transcending its biological roots entirely. Could life, as we know it, evolve into something that is not dependent on the physical universe as it currently exists? Some theories suggest that advanced civilizations, faced with the inevitable end of the physical universe, might find ways to escape the limitations of space and time. Could they upload their consciousness into digital forms or find ways to harness the quantum fabric of the universe to survive beyond its death? Such speculative ideas stretch the boundaries of what we think is possible, but the potential for life to evolve beyond its current biological constraints offers an interesting counterpoint to the traditional view of the heat death. While it remains a highly speculative concept, it forces us to reconsider what life means in a universe that is no longer capable of supporting life as we know it. As we contemplate the end of the universe, it's important to remember that the answers to these questions may not be within our reach, at least not yet. The universe is vast, and its future is shaped by forces and phenomena that we may not yet fully understand. As we observe the universe through our telescopes and develop our theories, we are only scratching the surface of its deeper mysteries. Whether the end of the universe will be a cold, lifeless void, or whether some form of life may survive in an altered, unimaginable state, is still an open question. But beyond the potential for life's survival in some form, the universe's end will likely be marked by the loss of structure and order. The galaxies that we now see so clearly will no longer be recognizable as they drift apart, no longer bound by gravitational forces. Stars will fade into black dwarfs, remnants of their once brilliant selves. Planets, stripped of the energy that once made them hospitable, will become frozen, lifeless rocks. Even the atoms themselves will eventually decay, breaking down into subatomic particles and radiation. This complete dissolution of structure from galaxies to atoms will be a slow process. In the vast stretches of time that remain, these changes will happen gradually, beyond the span of any individual lifetime, or even any civilization's existence. Yet, in the grand scheme of the universe, these events will mark the end of an era. The eventual fate of the universe is a paradox, a mystery that challenges both our scientific understanding and our philosophical imagination. As the universe reaches its final stages, we may never be able to fully comprehend what lies at the very edge of existence. Will it be a cosmic rebirth, a cold, dead end, or something else entirely? Only time will tell, and even then, it may not be an answer we can easily grasp. Time, as we experience it, is a constant and unyielding flow, one that moves in a linear fashion, past, present, future. Yet the universe itself operates on a much grander scale, where time is not just a constant, but a variable force that can stretch, bend, and even warp under extreme conditions. In this sense, the end of the universe may not be the same experience for all beings across the cosmos. The concept of time dilation, which occurs near massive objects like black holes, reveals that time is not universally experienced in the same way. To an observer far from a black hole, time appears to pass normally. But to someone near the event horizon, time slows down dramatically. This phenomenon, predicted by Einstein's theory of general relativity, gives us a glimpse into how time could behave in the farthest reaches of the universe. As the universe continues to expand, the time it takes for distant events to occur will become increasingly stretched, further displacing us from the events of the past. In the distant future, the nature of time itself may change dramatically. As galaxies move farther apart, the universe will become more isolated, and the progression of time could appear to slow down for those remaining. The lights of distant stars, which now provide us with glimpses into the past, will no longer shine brightly. Instead, they will fade, leaving only the faintest glimmer of the cosmic events that once were. We may one day look at the night sky and realize that the universe in all its grandeur has passed into a stage where time no longer holds the same significance. The future will be a realm where only the most distant echoes of time remain, a silent and almost imperceptible progression toward the inevitable end. But even as time fades, the legacy of the universe's existence will be written in the very fabric of its creation. The faintest remnants of stars and galaxies dispersed throughout space will remain as the only traces of a vibrant, ever-evolving cosmos. These remnants will eventually become all that remains, floating through an empty and still universe. It is here, in this quiet, isolated stretch of time, that we might find the true meaning of the universe's end. Not in a fiery explosion or a cataclysmic event, but in the slow, gradual fading away of everything we once knew. Yet, even in this fading, the universe will not truly be gone. It will continue to exist in the form of its history, written in the cosmic microwave background radiation, in the memory of stars and galaxies, and in the countless particles that once formed the building blocks of all matter. The final stages of the universe's existence may be a time of darkness and stillness, but it will also be a time of reflection, where we are reminded of the intricate beauty and complexity that existed, and perhaps still exists in some form. We must acknowledge that our understanding of the universe, while vast, is still just a glimpse of what truly lies beyond our perception. The universe, in all its complexity and scale, offers endless possibilities that we have only begun to explore. The question of what lies at the end of the universe is not just about the physical state of the cosmos, but also about our own place within it. As we reflect on the ideas and theories that we've explored, we find ourselves confronted with a profound realization. The universe, in all its expanse, is both a cosmic puzzle and a mirror, reflecting our own curiosity, our own quest for meaning, and our unceasing desire to understand. In this final stretch of time, as the universe continues to evolve, there will be no grand spectacle or cataclysmic ending, at least not in the way we often imagine. The end will be a slow, quiet process, an inevitable fading into darkness. The stars will burn out, galaxies will drift apart, and eventually, even the remnants of black holes will evaporate, leaving nothing but a cold, silent void. The beauty of the universe, in all its chaos and order, will dissipate, but its mysteries will live on in our minds and hearts, pushing us to continue asking the same fundamental questions. How did we get here? Where did we come from? And what, if anything, will come next? While the universe might end in a quiet, distant future, the legacy of our curiosity, our exploration, and our thirst for understanding will endure. It is through our pursuit of knowledge that we continue to redefine the boundaries of what is possible, whether it's in the realms of space exploration, theoretical physics, or the very understanding of the fabric of existence itself. The end of the universe might be a time when all observable phenomena have ceased, but it is in our questions and the answers we continue to seek that the true meaning of our existence will live on. As we look to the stars, we may never find definitive answers to the questions we've asked about the universe's ultimate fate. Perhaps, in the end, it's not the answers that matter, but the process, the journey of discovery itself. Just as the universe has expanded and evolved, so too will our understanding continue to unfold, revealing new insights and new mysteries along the way. Whether the universe reaches a final silent end or a new beginning, it is clear that the exploration of space and the mysteries it holds will continue to inspire us, challenge us, and shape our future. And so, as we lay down our thoughts on the end of the universe, we are reminded of one simple truth. The universe, vast and unknowable as it is, will always remain a source of wonder. Even when it seems to fade into darkness, it will live on in the curiosity and the spirit of exploration that resides within us all. The end of the universe may be inevitable, but it is also just the beginning of our eternal quest for understanding, stretching across time and space, always seeking, always reaching for something beyond the horizon.